And welcome to the iGuide VCO or Virtual Consulting Office series. Today, we will have a very interesting topic, which is on the bridging of high-performance computing and geospatial workflows. This was work done through OGC Testbed-19 and 20, work with iGuide as well as with OGC partners. Gerald was one of the key contributors to that effort. And Gerald is a founder of the Geo Labs, and this is a company which is specializing in geospatial solutions. And he has taken part in many of the OGC activities and has developed like a platform called ZOO-Project, which serves as a reference implementation of both OGC APIs and others. So today, I guess he will be talking to us about bridging high-performance computing and geospatial workflow based on the work that was done as part of that testbed. So without much further ado, I'll pass on the baton to Gerald. Thank you.
Hello everyone. So I will start by sharing my screen. Can you hear me okay, and can you properly see my screen?
Yes, both.
Fine. So I'm Gérald Faunois from the Geolabs company that has been founded in 2007, based in France. And I will present to you how did we re-implement or reorganize some iGuide workflows and encapsulate them in using a common workflow language by enabling us to deploy and execute the workflow remotely from an OGC API processes server. So first of all, I will introduce you the technology which is behind. So as introduced by Anand, we are relying on the ZOO project, which tend to be a software component that make open source software and any programming languages or libraries or applications available as WPS, Web Processing Service, or OGC API processes. So here is an overview of the ZOO project and its components. So we have in the core component, which is ZOO kernel, which is able to handle multiple programming languages, meaning that you can implement your ZOO services using, for example, Java, C, C++, or R. You can use directly this programming language to implement your own services. We later, along the way of developing the ZOO project and ZOO services, we decided that it was not enough to support multiple programming languages, but we were also willing to support already existing application catalogs, such as Orfeo Toolbox and Saga GIS, which are offering multiple and various GIS algorithms. Orfeo Toolbox being more focused on Earth observation, satellite imagery, while Saga GIS is covering both vector data and raster data. Also, along the way, we have implemented what we call the ZOO API, which is a JavaScript API that can be run on the server side. So using this and internally enabling internal invocation of C functions from the JavaScript world, we enable the chaining, complex chaining of services, as you can see on the bottom right of this slide, where we can, for example, chain GIDAL with GEOS libraries and invoke R for outputting some spreadsheet, for example, or some histogram. Also, we get involved in 2017 in, as I will talk a bit later, in implementing HPC service. We've been included in a European project, GeoSud and FIDIAS HPC, European project, that was targeting executing remotely HPC services, but as I will say a bit more later, it was unfortunately limited a lot to only offer toolbox application and to knowledge about the applications that you were willing to deploy on the HPC that needed to be available on this HPC. So to communicate also with this ZOO kernel, we implemented the ZOO client, which has become a bit obsolete because it was mainly focused on WPS version 1 and version 2. And since the beginning, I mean, since 2015 at least, we introduced the map server support internally into the ZOO kernel, meaning that for every ZOO services that is producing GIS data, it can be raster data or vector data, map server is used to spread your dataset using OGC web services, such as web map service, web feature service in case of vector dataset, and web map service, and the web coverage service in case of raster dataset, making your application, client application, able to not only interact with the processing engine, but also being able to easily show the result on a map. So the ZOO project is an OSGeo project. It incubated in 2014. And it is released under MIT X11 license, and it is implementing WPS 1, 2, and OGC API processes part 1 core. So actually, we do a bit more. We are also implementing the OGC API processes part 2 deploy, replace, and undeploy draft specifications that I will present today. We are also supporting partly OGC API processes part 3 workflows, specifically the remote process conformance class, meaning that you can use as an input the invocation of a remote process and create chain of processing this way. As I was mentioning earlier, the ZOO project supports dynamic loading and execution of services implemented in various programming languages. Here you have the list of the programming languages that are supported, and also the Orpho Toolbox and Saga GIS. Even if we have started initially with GraphGIS, we led this along the way by lack of support. So I will briefly introduce what is OGC API processes and how OGC has moved from service-oriented to resource-oriented. So the Open API specification, which is now the one conformance class, as we will see later on, one requirement for OGC API, at least we need to provide an API definition through the OGC APIs, and we can support the conformance class Open API, which specifies that you can plug multiple tools that are compatible and can use Open API standard. So Swagger was born in 2011, then the specification version 2 in 2014, while the Open API specification, which is the one we are using, in 2016, and I've moved the web services standards that I was mentioning earlier, such as web map service, web coverage service, and web feature services through web API. So you can see on the right hand side the multiple APIs provided by the OGC, such as OGC API features, OGC API common, that we will discuss a bit more later on, OGC API maps, OGC API records, processes, coverages, tiles, styles, and EDR. So OGC APIs are developed in part, which means that, for example, for OGC API features, you have multiple parts, and your server application or client application can be compatible and developed in parallel to support one or multiple parts. So also multiple parts can evolve in parallel, meaning that part 1 and part 3 can be modified along the year, but they can still be linked to each other, and they can evolve in parallel without hurting previously approved standard. So as we are discussing here today about OGC API processes, as any OGC APIs, it is relying on the OGC API common part 1 core standard, which is defining 5 requirement class. So the core requirement class, which says that it should be a web API. Then we have the landing page, meaning that you need to have a landing page for your API with at least these 3 links that are available on the slide. So the root, which is a landing page itself, / API, which is the API definition, which can be Open API or anything else, but in our case, we are only implementing the Open API support. And you also have the /conformance URL, which allow your client application to list the conformance class the server instance is conforming to. Then you have the encoding requirement class, which mention basically that you are communicating in JSON or in HTML, meaning that every request should be able to be accessed as a JSON, open application JSON, or an HTML page, making us able, for example, to implement a user interface linked to the OGC API. And then we have the OpenAPI 3.0 requirement class, which specifies that the API can be implemented as an Open API relying on the Open API specification version 3.0. About the OGC API processes part 1 core standard, which is standard defining how you can interact with the process catalog. So you will have, we are defining in this standard the requirement class core, defining that we have this following path that should be defined and accessible from your server instance. So you have the processes list, which is accessible using the HTTP GET method through the /processes path. Then you have the process description for an identified process ID. Then you can execute the process by posting an execute request to the processes /process ID /execution endpoint. If you are executing it asynchronously, you will then have location, link back, returned back, which point to the job status info, meaning that you can access to the /job ID to get the ongoing status of your execution, as we will see during the demonstration. Then you have a path to access to the job results, which is /job ID /results. We also have 2 requirement classes that will be presented today and that are supported by the ZOO project, which are the OGC API processes description, meaning that you are relying on this standard schema to output the process description, when you can also rely on OpenEO, for example. And you have also the conformance class callback, which says that if you are including some callbacks into your execute request, the server is responsible to then push information on the status update to the reference set callback from your execute request. Then we also have the requirement class job list, which make a client application able to list all the available jobs, meaning that all the jobs that are currently running or that has been run in the past. And then you have the requirement class dismiss, which make a client application or end user able to delete a job run and remove all its history, associated history. So about the ZOO project and its support for OGC API processes part 1 core, as you can see in these various screenshots, we have built up a basic HTML user interface, which is basically based on the JSON, which is outputted from the server instance, and it's converted into HTML user interface. We are currently providing a brand new user interface using Vue.js and Nuxt JS libraries. So the well-known technology, but unfortunately we realized that using this old school templating system was a bit more powerful, because we were able to take advantage of the internal support for natural languages, meaning that the ZOO project is able to speak in French, Japanese, Chinese, Czech, or English, which is the default language. And using this old templating system, we were able to take advantage of all the internal messages and all the service messages, while when moving to the new user interface, we realized that we have to implement the language support in a different way. You can see also the use of the WebSocket to have the ongoing status of a job run, of a job execution. We are also providing here an example of the Map Server 8 integration, which was done during the Testbed-19, which shows simply that as Map Server no support OGC API features, we are able to output the result of the execution of a service as a feature collection using the Map Server user interface based on OGC API features. And on the right hand side, you have the Swagger UI associated with this work that was done back in 2021. Along the way also we introduced the ZOO-FPM, which is responsible for executing the asynchronous task, meaning that the ZOO kernel is getting the execute request, send it to RabbitMQ to have another ZOO kernel which is client to this RabbitMQ, which is reading messages and pop up the processes manager as needed for the execution. And this permits actually to scale to multiple ZOO fast process manager. So I want also to introduce the common workflow language, which is CWL, in which is yet another markup language. It is actually giving you the capability to encapsulate command line tools or various complex workflow made of multiple steps. Here you have a very basic example of the docker.cwl, in which you have the CWL version, the class which can vary from workflow to command line to CWL expression or CWL workflow. You can define a bash command if your Docker file is not containing any bash command or any entry point. Then you have a requirement that can be ends with the Docker requirement, meaning pointing to the Docker image you are willing to use. You are defining then the inputs, the list of the inputs. So here we have a simple example, which is SRC, which is of type file, and input binding position 1 means that it should be the first parameter passed after this bash command. And the output in this example is the example out, which is of type stdout, and stdout is a text file which is named output.txt. So associating this Docker CWL with Docker job.yml, which is below and noted 2, we can give the parameter, so src which is a single parameter we have, and we pass, for example, an hello.js file. And to run this CWL with this parameter, you can simply run CWL tool, which is the official CWL runner. But as we will see later on today, we can use other runner to execute CWL in a various on different type of environment, for example, on a Kubernetes cluster or on HPC, relying on a different runner. And here you have the execution. So you are invoking a CWL tool with your CWL and your parameter, and you have the execution, which is run. And at the end, you can output the hello world string you have defined. So as mentioned, a process can be a command line tool, an expression tool, operation, or workflow. And we will see that this common workflow language was used in the best practice for Earth observation application package. On multiple slides, you have the QR code and the link also, which is pointing to this to the official documentation in case you are willing to have more details about this. But basically, the OGC best practice for Earth observation application package defines the best practice for packaging and deploying Earth observation application package encoded in CWL as CWL workflows in an exploitation platform. This is exactly what we will see later on during the demonstration. So about the OGC application package and its adoption, you can see a non-exhaustive list of projects that are relying on this OGC application package. So you can see, for example, the ESA-NASA joint multi-mission algorithms and analysis platform. You have also TerraDoué, which is involved in multiple projects, international ones, and also in EOEPCA. And also the work that will be presented today was first introduced by UK SFTC using the Jasmine HPC funded by the European Space Agency. So now that we know how to list processes, get information inside the process description, and execute processes synchronously or asynchronously, it is time to introduce you the OGC API processes part 2 deploy, replace, and in-deploy draft specification that I am co-authoring with other members of the OGC API processes suite. So it permits basically to deploy, as its name is clear enough, it makes you able to deploy, replace, and in-deploy processes on a server instance. So here you have a crossing table showing you the HTTP method and the resource endpoint you can use. So to deploy a process, you will post a process an OGC application package, that can be composed of a process description and an execution unit, or an OGC Earth observation application package, which is encoded as CWL. So this is for deploying a process. If you are willing to update, I would say, replace a process, replace the previously defined process, then you can send your OGC application package again using the put method on the process ID, because you now have a process ID because you have deployed it in the first step. And you can then, and you can then undeploy the process using the delete method and the resource endpoint, which is process ID. So about the encoding that I was referring to, we have multiple encoding. So we have the OGC application package, which is basically the process an JSON object composed of process description and an execution unit. This was the first try we made during the Testbed-19 that I will show later on. We defined a specific attribute in the execution unit to specify that the execution should occur on HPC, but it was very limited. Then we have Docker encoding. This is not supported by the ZOO-Project. And finally, we have the CWL, Common Workflow Language, meaning that you can directly upload your CWL as is and create a process and make it available on your server instance. So the ZOO project and its support for OGC API processes part 2 deploy, replace and undeploy, so DRU, was funded by the European Space Agency through the EOEPCA, Earth Observation Exploitation Platform Common Architecture. EOEPCA was the first project, and then we are currently in EOEPCA Plus, which is including other components in the platform. So ZOO-Project is actually used to, with this implementation, I would say that the ZOO-Project changed the way it handled processing, meaning that initially we were basically downloading the data, processing the data and providing the result. While with this capability of deploy, replace and undeploy, we are now able to deploy the application package where the data is, for example, on Amazon Cloud or Google Cloud, and avoid making the data transiting from one end to the other, reducing the cost, basically, to move data from one cloud provider to another one. So you can access the official ZOO-Project-DRU Helm chart, which is available on Artifact Hub. And as you can see on the right side, the idea is that you can run multiple runners. So currently we are supporting Calrissian, which make your CWL able to be executed on a Kubernetes cluster. While I will show you today the Toil WES Workflow Execution Service implementation, which enable you to use the exact same CWL that you were using on Calrissian and running on your Kubernetes cluster, running on HPC remotely. And we also have nowadays an integration with Argo Workflow, meaning that you can deploy your CWL and an Argo Workflow template will be using it to execute it as an Argo Workflow. So here you have an overview of the runner we are supporting currently. So we have started with ZOO Calrissian runner, where you can see here the deploy and the execute operation. So when you are requesting to deploy a process on the server instance, you will the ZOO project behind the scene will basically clone a GitHub repository where the service template is located, and instantiate this template to create a service instance. And then when you will execute a process, this service.py associated with the original application package in CWL format will use the ZOO Calrissian runner to invoke pCalrissian, which will then execute a Calrissian image on your Kubernetes cluster and will make every step popping as an independent pod, potentially running on multiple nodes. So here is the result of the experiment we made in Testbed-19 in High-Performance Geospatial Computing back in 2023. So the idea here was to try to reuse OGC API processes part 2 deploy, replace and undeploy, and the OGC application package JSON format to enable the deployment of the process through the ZOO project. And this was involving, as you can see here, a dedicated operation which is named deploy on HPC, which was run asynchronously thanks to the ZOO FPMUs, which was actually converting the Docker image into Singularity and making it available on a dedicated place on the HPC. And then the process summary was returned back to the client. As you can see on the right-hand side, inside the process description, we were forced to have some kind of binding between the inputs that are defined in your process description and the input that your workflow is willing to use. And for example, we added an additional parameter which is named entry point, simply to point out the singularity command that should be run and executed on the HPC. Also, you can see in the execution unit that the type was Docker, as defined in the DRU draft specific deploy, replace, and undeploy draft specification. But we added the deployment keyword to the schema to enable the capability to detect where the deployment should happen. Actually, it was only made for HPC, but it was simply to illustrate that the draft specification can be extended, and this deployment key is now available in the official schema, so it can be used. But unfortunately, it was reducing the capability compared to CWL, to what you can do with CWL, where you can encapsulate a complex workflow using a scatter method to bind input to a dedicated process and then pass this to other processes. And here we needed to define our own additional parameter, and it was, in our opinion, a lack of time to implement all this, but at least it was good to learn that this limitation was there. Just to, before we move on to the dedicated HPC stuff, I was willing to point and was introducing in the beginning that we get involved in GeoSud and FIDIAS HPC EU European project. It was actually the initial steps toward HPC support and toward our knowledge in HPC and how it works. So it was basically using the same technology as here, meaning that we were producing the S-batch remotely on the ZOO kernel, on the ZOO-Project server, and then we uploaded this on the Slurm, on the HPC cluster, on the login node, actually. Then we invoked Slurm to execute this S-batch, but as said earlier, we have all this binding between the input and the final execution, which is written inside the S-batch script, which is then uploaded, which is too tedious to maintain. Hopefully, with work led by the EOEPCA in the EOEPCA Plus project, we introduced the ZOO WES runner, so which is relying on the Toil Workflow Execution Service, which is made by Santa Cruz University in the US, and it can be used to, it can use Slurm as a backend for the execution. Actually, we are also using it in a very different way, meaning that you can use Slurm, but if you are willing to execute the CWL using Toil on your personal computer, you are also able to do so, and also to use the backend, which can be Kubernetes. So basically, as you can see here, it is exactly what we had already in the ZOO Calrissian runner, meaning for the deployment, we still have this service template which is instantiated and to create a service instance. Then when you are executing the process, the service.py reuse the application package and simply send it with the parameter to the Toil WES server, which is then responsible to schedule and execute tasks on the HPC. This was also part of the work done in the Testbed-20, High-Performance Geospatial Computing, in the Testbed-20 activity back last year, 2024. So this is actually the infrastructure which is currently available, which has also been replicated in DLR infrastructure, which is a German space agency, which is also providing us with HPC resources specifically for the EOEPCA work. And we have set up this specific platform also for their own purpose and for their own use. So basically the client will connect to the ZOO-Project-DRU, which is running on a Kubernetes cluster. We have an S3 bucket which can be stored actually in the same Kubernetes cluster or anywhere in any other Kubernetes cluster. The current limitation in our implementation is that Toil WES RabbitMQ and Toil Celery Worker are both working on the Anvil SSH login node, meaning that the administrator to set up this infrastructure need to set up to a single login node. So you identify one of the logging node you are logging into, and then you should deploy all these services on the same login node for enabling them to communicate between each other. So the ZOO project is connected using SSH tunneling to Toil WES to access port 8080, because on HPC you are not allowed to expose any service outside of the HPC. So this is why we are relying on this SSH tunneling. Then the Toil WES receiving an execute request, basically a CWL and parameter, like as we see earlier when I was showing you the CWL tool invocation. Then it send a message to RabbitMQ, and Toil Celery worker will take the responsibility to invoke Slurm using the Toil Python module. So in our study, we have implemented the algorithms, which is a vulnerability analyzing aging dam, which is available as a Jupyter notebook online. So actually the issue we got initially was that we don't have much more knowledge on the workflow itself, but we are thinking that it will be great to enhance the granularity, meaning that we can probably split the full workflow into smaller tasks, because as I will show you later, we can actually parallelize some tasks and using CWL directly. So we don't have to reinvent anything. We simply have to define some scattering method on inputs and the way they need to be outputted to be gathered together. So also during the work we handled, we had multiple requirements for data. These data were not always available during the period of our study. So what we did was that when the data became available again, we decided to make a copy of all these data sets and host them on our S3 bucket. This way we were also able to compare using various COG partitioning and sizing. We were able to compare using the same S3 bucket the time of execution, meaning that the time to consume the data was the same because the S3 bucket and the source was the same for the download. Also, there is no and there is still no automatic conversion from GeoEDF, which is the paradigm that is used in iGuide to be converted into CWL. But HPCCM, which is a tool made by NVIDIA, we were able to convert the recipe file into a traditional Docker file and then build this Docker file and publish it on Docker Hub to finally get it downloaded from the HPC at execution time, which is automatically using Toil, which is automatically converting this Docker image as a CIF image, singularity image, that can be then used and invoked from within the CWL workflow. We would like to point out also that building the Docker image for the full workflow is a slow process, and we probably rely multiple times on the processes that are included in the full workflow. And as we did not split it up, we cannot take more advantage of the parallelization, but this may be the next step for this implementation. Also, yes, issue with login nodes I was mentioning earlier already. About the summary and recommendation, so CWL is reliable for parallel processing. I will illustrate this in the demonstration by using the scatter property on a single input. This way you can have one input, or you can run the algorithms on one DAM or on a list of DAM, and all this DAM processing will be run in parallel without the need of you working or modifying anything from your initial CWL. So CyberGIS compute relies on HPCCM, as you know, recipe from NVIDIA, and it can be converted into a Docker file. ZOO-Project-DRU implementation of the OGC API processes part 2 deploy, replace, and undeploy draft specification has demonstrated that it is possible to deploy and execute CWL on remote HPC using Slurm and Singularity, what I will show you in a minute. We also review how to distinguish where the Earth observation application should be deployed and run when encoded as pure CWL, because you can also run it from command line, meaning that you don't need to use the OGC application package JSON format. We also need to review how Toil WES is set up to properly pass parameter with distinct parameter for every run. For example, we have tried to integrate this Toil WES with provenance, because CWL is supporting provenance recording using the W3C prov ontology, meaning that you are able to access the full provenance of an execution of the process. But unfortunately, we realize that by doing so, that every time Toil is invoked, we cannot parameterize parameters that are passed, except by modifying the code of Toil itself, but it was not our goal, so we escape this. And also we are currently on the way to review how the multiple building blocks are set up, meaning that we are now able to run ZOO-Project, Toil WES, RabbitMQ on the same server, and only the Toil celery same login node. If there is any question, we can go, you can go and ask them, or in other case, I will move on to the demonstration now.
Any questions now before we go to the demo?
To stop sharing. Stop sharing. And can I share this screen? This window. Oh, somebody.
I think it's not a question.
Excuse me.
Yeah, go ahead, and I guess we can start with the demo and then see if there are other questions.
Or in other case, what I can do is, as before, like this, and then put this here. Okay, and then
Maybe you can make it slightly bigger. I guess we can see
yes,
the screen.
absolutely.
Yep, great, thank you.
So here is a demonstration I have set up a few hours before the today's meeting. So as you can see, it is running on my local Minikube cluster. Okay. So what I've deployed is, as I was mentioning earlier, is a ZOO-Project-DRU. Okay. So the ZOO-Project-DRU come with expose an open API. So this Open API is compliant with OGC API processes part 1 core, and it's actually a reference implementation for it. So you have the multiple endpoint I was mentioning earlier. Okay, I moved to another window. Okay, so here you have the landing page. Oh, I'm sorry. I was mentioning earlier that the ZOO project is supporting various natural languages, and my environment is configured to speak in French. So you may see some strings that are converted only partially because some specific sentences are only available in some specific ZOO project setup, so not everything is fully translated. We are not 100% translated. But anyway, so here you have the basic slash conformance and API endpoint I was mentioning earlier, which are defined in OGC API common core, part 1 core. So then you have the list of processes that are available. And in this using this specific endpoint, which is using the HTTP post method, using the path processes, you can deploy, as I was mentioning earlier, a CWL. When I say deploy a CWL, meaning that you are simply copying and pasting any CWL you have at hand, and you can deploy it as an OGC API processes service. So in this example, we have two inputs. We have the DAM ID array. So you see the label and documentation that can be added and associated with an input. And you then have the type, which in this case is of type string, array of string. Okay, so this in case you would have an interrogation mark. I'm sorry, I'm using Apple. In case you would have used an interrogation mark here, it would mean that it's a string, array of string, or an empty, or you are not forced to. This is an optional input, basically. Then you have the URL, which is a simple string, and the output is named stack in this example, and it's an array of directory. What is important here is that we are using this scatter feature requirement, and you can see that in the steps that are involved in this CWL workflow, we have only a single step, which is our iGuide processor. So in this step 1, we are mentioning that as input, we are providing DAM ID, which is coming from the DAM ID array, and the URL, which is coming from the URL initially provided in the workflow. And then we are willing to run the process, which is this ID here, which is then a command line tool because it's a graph. So you have you can encapsulate multiple elements in your graph and then invoke them using their identifier like this. And here we are saying that we are willing to scatter the DAM ID using the scatter method dot product, meaning that in case you are sending a single DAM ID, it will invoke this command line tool, and in case you are providing an array of DAM ID, it will run this process in parallel and then return back the output using this dot product method. You have the scatter documentation for CWL available online. So once you are posting this, I already did it earlier, so I won't do it again. So you are basically posting this CWL as is, okay? Mentioning in the header that the content type of your request body is CWL plus YML format. Then the response returned back is 201 status code. with, I'm sorry for this scrolling issue. Up. It is because I'm using an Apple mouse on a Linux platform. So here we have the, okay, so if we go back first to the initial CWL, what you can see is the identifier of the workflow, the identifier of the workflow. So it is named extract inundation census track. And we can see that the process is named using this exact same identifier. Title and description will correspond to the label and documentation of the workflow itself. You can obviously reference any schema.org provenance information, such as the maintainer of the software or the software version and so on. You have all this defined and pre-cooked for you in the Earth observation best practice I was mentioning earlier. So then in this basic process summary, we are also seeing that the process is mutable. Mutable is a Boolean value that can be false or true, meaning that all the services that are already available when you are deploying your ZOO project are typically not mutable, meaning that they are coming with the ZOO project itself, while the deployed processes have this mutable parameter set to true. Then you have the version of the application, which was stored in the schema.org software version of the initial CWL. Then you have the output transmission, meaning that your process can output the value as value or reference, meaning that you can output a full feature collection or reference to this feature collection, for example. The job control option, the job control option can be async execute, meaning that you can run this process asynchronously. Usually you also have the sync execute, but it's not listed in this job control because you are mutable equal to true, meaning that you have deployed the process, and meaning in most cases that it will be a long running process, so it will take time to give you back a result. This is why we are forcing the end user to use only the async execute. And then you have a link which is pointing you to the location of the execution endpoint. So actually, if we go to this execution endpoint, also we can have access, you can have access to the process description, so the full process description, not only the summary of the process. So you have basically getting back the same process summary again, but this time you will have all the details about the inputs. So for example, the DAM array, which is, which is of, which has a schema associated with it, mentioning that it is an array of string. You can see also the max occurs, which is equal to 1999, meaning that there is no limit actually for this array in size, despite we are defining one value. Then you have the URL, which is in the same way associated with a schema, which is defining what is the type of the URL, which is of type string in this case. And also, I don't show you, but you have the output, the result, right, which is stack. So as you can see in the original schema we were providing initially, we are simply mentioning that it is a stack collection using this stack collection schema. But lately we have integrated CWL to OGC, which is a Python library which makes us able to convert CWL and specific CWL custom types into valid OGC API processes, which is making our schema a bit more complex than earlier, meaning that in the schema for the output, you will basically have the full stack collection schema integrated here. So we won't go deep in this, but you So now, if we try to execute it with one DAM or another, so for instance here I was trying with this DAM ID which was in Texas number three, so I now move to Texas number 2. Then the URL is the location where this where the COG data will be downloaded. So here, as I was mentioning earlier, I am using an internal, publicly available S3 bucket. Okay, actually in the CWL, in the CWL, we can see encapsulated in the development and the environment variable. I can show you that we are encapsulating our authentication method. So here in the CWL, in the command line tool, we are able to define any environment variable using the env requirement, where we are defining environment variable using this envdef object, in which for this example we are providing the AWS S3 endpoint, which is a testbed-20 geolabs.fr node that has been set up just for this today demonstration with AWS access key and secret access key, which make us able to download the data from this S3 bucket. This is why we can say, okay, I want the data to be downloaded from this VSES3, which is basically the GIDAL notation for VSE, virtual file system, and the S3 specifically virtual file system for S3 bucket. So now here was a previous run, so I will still keep this job ID. Up. And if I execute, so I start the execution of a new process. So here what I get back is basically a location where I can fetch status information. So I can simply use the job ID, which is the ID of the job status, and use it to see what is currently happening and what is the current status of the execution. So the ZOO project tells me that the job is currently running on the HPC. What is funny is that I can, sorry, here you cannot read obviously. So I am actually logged on the HPC server. Here you can see the Celery worker, which is invoking this Toil CWL runner with the batch system, which is Slurm. Okay, here are the parameters generated automatically by Toil to store the various information like the messages, and you can also follow up from this. If you take a look into the last test file, so this is where the one we just started, and you can actually, for example, review what is happening like this. So Toil is invoking the extract inundation census track process, and also you can check what is happening here. So here I have invoked the CWL with only one single input, but in case you are providing an array of input, you will have the number of parallel tasks corresponding to the number of inputs until the resources are available at runtime on the HPC. Also here you can see this is sorry, this is the Celery. No, this is the toilet. And here we can wait to have the result, but as I saved earlier already few results, I can show you previous run we've made. And typically at the end of the execution, but we will have the same in a few minutes from now, you will have a feature collection which is containing all the output of the workflow execution that can then be downloaded from the S3 bucket and shown on the map using different classification as illustrated and presented in the Edging DAM Jupyter notebook that was initially converted into CWL. And now, if I simply go back here, upload, and wait for it to complete. And just for your information, actually the toil command you have seen here can also be copied and pasted inside your terminal from any HPC logging node to execute this full featured job. But what you have to understand is that if it's easy to run the initial workflow that we have deployed, here it is a bit more complex because we are creating a more complex workflow containing potentially staging for directories in case you are pointing to stack item or stack collection. You also have the capability to stage in files, and at the end of the graph we are also outputting adding a stage out, which is responsible to get any result you are producing and push it on a dedicated S3 bucket using the additional parameters that you can set when you are setting up the ZOO-Project-DRU on your Kubernetes cluster. Actually, the deployment is really straightforward nowadays because we are relying on a scaffold system. Can I make it bigger? No, I can't. Okay. And basically, you simply run one command scaffold dev minus WES, and obviously you have to set up a few other things like your S3 bucket and everything. But once you have all your settings, you can simply reuse this pre-parameterized configuration and deploy it in a matter of minutes. So finally, we can see here that the state of the execution is completed on the HPC. We can also see the logs here. So these are the typical log when you are executing this Edging DAM detection workflow. And at the end, as I was mentioning, we are generating very basic stack catalog containing all our 3 results. And we are storing it on our S3 bucket. So let me go back first to this and see if it is finally successful. So you can see that the execution went off well. Okay, and now if I take this job ID again and I try to access the result, then I will get my feature collection with this dataset and what I have with this GeoJSON dataset, output dataset. Here I have my S3 bucket available from the web, so I can download this dataset. And while I have downloaded this dataset, I can include it, add it to my favorite tool. So this is the one I just created. Okay, close. is it? Okay, I have 2 times the same. I guess I will be.
Gerald, I think this is great. I wanted to check with the audience if they have any questions at this point. Maybe since we are running out of time. I do have one question though. Like, I think this is wonderful. I think, but you had many of these services deployed on your local host environment. So, is there a plan to make this kind of as a service available to the larger audience and maybe sharing it with some of the people who might be doing research with?
Absolutely, because actually CWL is also providing and enabling you to reproduce an experiment, meaning that once you have encapsulated your workflow into a CWL, you are able to replicate the same execution again and again on various environments. So obviously we can make a public application, but it will require user authentication, and I think we are not allowed to how to say, to share the HPC resources that was allocated to us by the iGuide team
Yeah.
to the wider audience. But in other case, you can typically do what I did today: download the ZOO-Project-DRU from Artifact Hub
Okay.
and deploy it on your own Kubernetes cluster. This way, you will be able to handle the security by yourself, but you should know that the ZOO-Project-DRU is supporting also OpenID Connect
Mm.
method to authenticate its user. And during the testbed 19 and 20, what we did was that we allowed all the participants from the testbed activity to their user to access and use the HPC resources. The only limitation to make this application public is currently the capability to share these HPC resources with foreign users. Maybe if we set up something like a registration protocol, this way you can check whether or not you are willing to allow this user to use your HPC resources. Then it will make sense, but this is actually why this user interface and Swagger UI was not published specifically for this testbed 20 activity.
Okay.
But it was done for DLR, as I told you,
Yeah.
for the internal testing.
Wonderful. Thank you. Maybe do we have any other questions for Gerald?
Not really, just to say it was really interesting and a lot to digest. So thank you for sharing.
Thank you.
Thank you. Yeah. Wonderful. I think Gerald, is this kind of, do you have other things to share as well, or is it like we can wrap up?
I think we can wrap up. I was just showing here that the results that I was showing earlier can also be then integrated in full stack catalog. You know, the stack catalog, the static stack catalog I was providing. It can then be used using stack browser to browse it, and we also are including the provenance information about where this data was processed and by what kind of software was involved in the execution. This was done in another activity during the testbed 20. This is it. Thank you for your time.
Thank you.
And for giving me the opportunity to present today.
Thank you so much, Gerald, for the presentation. This was really helpful and knowledgeable, new things that we learned here. So thank you for that. And thank you everyone for attending and staying for the whole hour. We will see you in one of the other iGuide VCOs soon. So we have this typically every week on various topics. So we'd love to see that. See you all soon. And again, thank you, Gerald and others.